For section 5.1, we're verifying identities. So our essential question is, how can I use, recognize, and simplify trigonometric expressions to verify identities are true? And so I underline this just to reiterate that identities are always true, and our job is just to show that they're true. Okay? So trig identities are trig equations that are always true for all x values. So we can plug in any x value we want, and we're always going to get an equivalency. To verify trig identities means to show that the equation is true. And trig identities, again, I'll say are always true. There's no question about it. We're not determining whether it's true or not. We're showing, we're verifying that they are true. Okay? That's the nice part about trig identities is we know what the answer is supposed to look like in the end. We're just verifying. Okay, so some tips we're going to use are going to sound like section 5.1, which is we're simplifying, but we're going to work on one side at a time. Okay, so we don't want to try to add to both sides or multiply on both sides. We want to work on one side at a time because remember, we're trying to verify that the two expressions are equal. Okay, so we're going to start with the most complicated side, right? Use fundamental trig identities that we looked at in the previous section. If possible, we're going to factor to simplify. And then also we're going to rewrite trig functions in terms of sine and cosine, just because those are usually easier to recognize, and then we can use identities after that. And then one last tip is just keep checking the other side to see if we're getting close to what we need. We know what the answer is supposed to be. We need to just make sure we're getting closer and closer to that expression. Okay, so let's look at some examples. All right, so our first example says verify the trig identities. And we have secant y times cosine y equals 1. So in this case, our theta, our angle, is labeled as y. Remember, any variable is fine to use for your angle. So cosine times secant times cosine equals 1. All right. So what I'm going to do is rewrite secant in terms of sine or cosine. And we know that secant is the reciprocal of cosine, so I'm going to rewrite it as 1 over cosine. Because cosine here is already written in terms of cosine itself, I don't need to change it. So I'm just going to rewrite it as cosine y. Our job is to show that this expression equals 1. So I'm going to highlight what I want to get in the end, and I'm just going to keep reminding myself I'm trying to get closer and closer to the answer of 1. So 1 over cosine times cosine, if I think of this as cosine over 1, now I have cosine over cosine, which just simplifies down to 1. Right? The cosines cancel out. I end up with 1 as my expression on the left side, and because that is exactly equal to the expression on the right side, I can say I have verified the identity. Yes, secant times cosine equals 1. Okay, let's look at our next example. We have cosine squared minus sine squared equals 2 cosine squared minus 1. Now, a lot of times when I read the equations, I leave out the angle just because the angle's there. It's going to be there and it has to be there. The more we say beta or alpha or y, whatever the angle might be, the more we kind of get confused sometimes. So we'll just say we have a cosine squared minus sine squared equals 2 cosine squared minus 1. Generally, we want to work on the side that looks harder. Sometimes the sides look equivalent. Sometimes both sides look difficult, right? Or they don't really look like one is harder than the other. In those cases, you just get to kind of choose. So I'm going to work on the left side, and I want to try to get the left side to equal 2 cosine squared minus 1. Okay. The left side's already in terms of sine and cosine, so I can't really change them in that sense, but I can look at my fundamental trig identities and say, well, what do I have that I can maybe exchange? Okay. Because I have cosine and sine squared, I know I'm going to probably use a Pythagorean identity. Okay. And also because my answer that I'm looking for only involves cosines, I want to try to get this sine squared out of there. Okay. So let me look at the Pythagorean identities and see what I can find. So from 5.1, we see that sine squared plus cosine squared equals 1. Okay. And we rewrote that in a couple of ways. we rewrote it as cosine squared equals 1 minus sine squared, and then sine squared equals 1 minus cos squared. Because I'm trying to get rid of sine squared, I need to find what sine squared is equivalent to. It's equivalent to 1 minus cos squared, so this is the identity that I'm going to use. So I'm going to rewrite sine squared as 1 minus cos squared. So cos squared is fine to stay, minus, it's sine squared that's going to change to 1 minus cos squared, thanks to the Pythagorean identity. And now I've rewritten sine squared, and now I'm just going to do my algebra. I have cosine squared minus this quantity, so I'm just going to distribute that negative in, and that now means I have cosine squared minus 1 minus negative cosine squared, so plus cosine squared b. Okay, and so now I'm again using my algebra. I have cosine squared plus cosine squared. They're like terms, so I have 2 cosine squareds. It's supposed to be squared minus 1. And I could keep going, but if I remember to keep looking back at what I want 2 cosine squared minus 1. And that's exactly where I'm at. So I can stop. I can check off that I have verified that identity. The left side is equivalent to the right side. Okay, so let's look at another example. 1 plus tan beta equals secant squared beta over tan beta. Now, left and right sides might not look like one is more complex, but I would say anytime we have a fraction, it's usually better to start with that side. They both have fractions, but this one's a little less simplified. Okay, there's a fraction plus a whole number. So what I'm going to do is try to change this so that I have just one complete fraction, right? Get common denominators, and try to verify that it equals secant squared over tangent. Okay, so I have 1 over tangent beta plus tangent beta, but I can rewrite that as tangent beta over 1. Okay, and so common denominators. I have a denominator of tangent. I have a denominator of 1. My common denominator would just be tangent. So I'm going to change this guy so that it has the denominator that I want. I'm going to multiply numerator and denominator by tan b. So now I have 1 over tan. I always had that. Plus tan times tan on the numerator, so tan squared, over 1 times tan, so tan. Okay, now I have common denominators. I can add my numerators, and really adding them is just kind of pushing them together since they're not like terms. So 1 plus tan squared over tan. Still trying to verify that it equals secant squared over tan. It's nice to know what my answer is supposed to look like, because I know I already have the right denominator. Now I'm trying to change the numerator. 1 plus tan squared. How can I rewrite that? Because it's tan squared, I'm going to look at my identities and say, what identity involves tangent squared? The second Pythagorean identity here. 1 plus tan squared equals secant squared. So that's exactly what I'm going to use. I have 1 plus tan. I'm going to replace it with secant squared since they're equivalent. So 1 plus tan squared is the same as secant squared. I don't need to do anything to my denominator since it's already what I want. And now I have my left side is exactly equivalent to my right side. Nice to put that little check mark so we know we're done, and we know we've shown that the left side equals the right side. All right, let's try one more. Okay, so there's a little typo here. Put this in parentheses. So really what we have is 1 plus sine y, y is our angle, times 1 plus sine of negative y equals cosine squared y. Okay, so it's really clear that the left side is more complex than the right side. So we're going to work on the left side. And I have one piece that I can quickly change. I have sine of a negative angle. We're going to use the even and odd identities to change that. And then we'll do a little algebra. So I have sine of a negative angle, and that equals negative sine. So instead of having that angle be negative, I'm just going to write it as negative sine of the angle. So this guy right here is going to be negative sine y. Everything else will stay the same. So 1 plus sine y times 1 now minus sine y. I'm trying to show that it equals cosine squared y. So let's do some algebra. I have a binomial times another binomial. I can just multiply them together. 1 times 1. 1 times negative sine is negative sine. And sine times 1 is sine. Those will cancel out. Right? These are the exact same terms, except the sign in the middle is different. Right? The positive and the negative. So the middle terms are going to cancel out. You could write it all out if you wish. Okay, so that you can see the middle terms will cancel out. And then I have sine times negative sine, so negative sine squared. Okay, and now that I've simplified, I can say, well, let me go back to my trig identities. I see a squared term, sine squared, so I'm going to go back and say, which of these Pythagorean identities involves sine squared? We know that one, it's sine squared plus cos squared. But if I go down to where we rewrote these, I can see that sine squared equals 1 minus cos squared, or cosine squared equals 1 minus sine squared. So if I look at what I have 1 minus sine squared. So I'm going to use this identity here and say, well, that is equivalent to cos squared. And that's exactly what I wanted to show, that the left side equals cosine squared, just like the right side, and I have shown that. So that is complete. Okay, so try a couple problems and then look at the next video for a little bit more complex trig identities.